So you want to become a robotic software engineer because robots are cool and software is cool. But there's so many jobs out there with so many qualifications. How can you possibly be good enough at everything to be able to get the job by the time you want? So I broke it down into 19 different types of robotic software engineers that each have their own category and their own particular set of skills so that you can kind of evaluate and see which one strikes your interest most or which one aligns with your skills most. So you can only focus on the skills necessary for that job. So I guess I kind of have two bonus of two different types of categories that'll be towards the end, so stick around for the whole thing. Now I gotta add the caveats that not every company will have these divisions of software engineers. Some of them will be combined, some of them will be separated even more if you're at a really big company who have like very particular specializations. Take this with a grain of salt. I'm trying to give a decent generalization. So I will say there are some skills for core robotic software engineering that are pretty applicable to many of these, and that'll be C++ and Python are commonly the most used programming languages. I've also heard of C# and Java, but they're far less common. I mean, when you're doing C++ development, you need to be able to compile your code, and that may be with ROS. If you're using a robotic operating system, that's a very common tool that you want to be able to use. Things you get for ROS are like the transform tree and the messaging system and visualization tools. So if you don't use ROS, you want to look somewhere else for being able to implement those types of things. You might use protobuf messaging and MQTT, or is there another better visualization tool? ROS crashes periodically, but generally I've either seen the ROS visualization tool or you write your own. Same with transform tree. You either use ROS or you write your own, and that's a lot of work, so a lot of people just use ROS. Thank you to the ROS developers. Linux development is also very, very prevalent. Rarely you'll see people developing on Windows, and sometimes you'll have RTOS, like real-time operating systems, where your system really needs to be deterministic, like an aircraft. You can't just let it fail, it'll fall out of the sky. Let's talk about each of the categories. Localization is the problem of where is your robot, and you'll generally use the sensors that you have to help you determine where that is. So you may have IMU, you may have camera for visual odometry, you'll commonly use point clouds to be able to create a map beforehand and be able to match your map up with where you are right now. You'll need to be really good at writing algorithms and good quality code. C++ is very common because you need it to be able to run fast enough to run on your system. You'll generally want to be comfortable with multi-threaded algorithms, developing in Linux, and being familiar and comfortable with processing sensor information. You need to be good at math, so linear algebra for the transforms, probability for state estimation, which gets into you need to be very familiar with state estimation algorithms. The Kalman filter, the extended Kalman filter, and the unscented Kalman filter, because EKF stinks. They got comical, yeah. Is a very, very common algorithm because it's run in real time and doesn't need to keep a lot of memory. Particle filter maintains more memory, but it can also have multimodal states. So there's different reasons why you might pick one over the other. But having implemented Kalman filter or particle filter in a project definitely helps get you more qualified for being able to work on that problem for being a robotic software engineer in localization. If you like really tough challenges, hard to solve problems, because it is very common to have errors that you're just scratching your head going, I have no idea what's going on. I've worked on this problem and it's definitely happened. So if you like the hardest challenges of debugging, then this might be a good fit. Mapping. This is probably one of the most physically active other than testing. So if you really like walking around, seeing a space, writing algorithms, and kind of like seeing how your stuff affects the scene around you, then that might be a good fit. So I will say that localization and mapping are commonly put into the same category, SLAM, simultaneous localization and mapping, but sometimes they'll be broken up. So the purpose of mapping is localization. Mapping is basically having your robot go out and collect the information of the space that you intend to run your robot in, so that you can establish and kind of clean up sensor information that you can then store in a way that you can later load and be able to say, okay, I'm getting this current sensor information, I can compare that to the map that I previously stored and say, yes, this is where I think I am. If you're working with an online localization and you don't do pre-mapping, you may not even have a mapping department. Sometimes you'll have different groups where you'll be able to run factor graphs, in one area, but you may not be able to run that online. So some of the same skills that are applicable to mapping are the C++, writing algorithms, being very familiar with mathematics like linear algebra for transforms and probability. You'll likely need to write some bash scripts. You'll often have to be good at cloud because you want some type of data management and maybe compression. You'll generally need to keep it in a submap type of form because it takes up so much space, so you can't keep all of the information in memory. Point clouds are enormous. So the most common clouds are either AWS or Google. That's what most people use. I will say that like the mapping and localization, the SLAM problem, is something that is highly sought after, and there are never enough engineers. So if you're really good at math, really good at algorithms, and you just want to pick something to be able to go into that you can have a little bit more reliability if you get the experience in, I would definitely recommend SLAM and localization because they're always needed. DevOps. DevOps is like the oil to a car. You need it to be able to run. You don't think about it, you just always have it. But if you don't have it, then it like completely crashes the car and nothing can run. So you really appreciate when you have things running well. What DevOps is basically creating an environment where the whole system can run properly. Making sure that logs are being recorded, making sure that things are being uploaded to the cloud, making sure that the system itself is able to run, maybe running Docker containers, having things start up, on startup, having proper security measures. That's definitely important. You want to make sure that nothing is being stolen while it's being sent off or is able to be hacked into. So for cloud processes, you might need AWS or Google Cloud. Linter, know what linter is. Setting up linter can be useful for making sure the code is all cohesive and looking in the same format, and that can be an automated Jenkins system for when you merge back into Git. There's certain things that you can do for version control. When everyone's making their change on their branches, then they'll want to be able to push things up. And when it's ready and properly tested, then they'll say they want to merge to the master branch or the main branch. But you can do certain checks to automate tests and make sure that, okay, everything's still built, so yes, you can go ahead and make your merge into the master branch. You'll hopefully have code reviews. You can automate making sure that somebody else has approved that branch. Sometimes something breaks. You change something, you don't realize it affects something else, something breaks on master, and then if it's broken on master, then everybody else tries to run their stuff. They can't because the master's broken. But you can revert. It's just, you don't want to have that time in between, oh no, who broke master? And you got to go back and change it, and better to avoid those situations. I've even heard sometimes if you break master, you have to like bring everybody donuts or something. So that incentivizes people to go through their own steps of automation and checking. Jenkins can be a really useful tool for basically setting up things to be able to run every day at a certain time. If you want to make sure that every night at 11 p.m. a set of tests based on the latest master is kicked off to say, okay, everything that we expect to run, maybe in simulation or maybe in unit testing, is able to run in a proper way. And that just really allows you to find errors and bugs sooner than you would normally. If you can't deploy things to your robotic system, then you can't run things. If you can't take things off of your robotic system and analyze, you can't fix things. If you can't keep running tests, then you can't catch things. So now we get into human-computer interfacing. So this one gets more into like intuition of people, which gets interesting. Like, it's not just straight, okay, program it to do this and this is what happens. Like, there's been a lot of times where I've worked with robots and it's like, all right, we want to indicate to people that we're going to do this. Like, okay, we're about to cross the road. And what indications are most intuitive for people to understand? Like lights showing, okay, we're going this way, or like a big blinking thing. I don't know. Sometimes it's trial and error. Sometimes it's like interviewing other people and asking other people. So you definitely want to have the people skills. If you've had a lot of like microcontroller interaction and work, then this might be a good fit. This is another one where if you really like to program something and see a reaction, then this could be a good fit. Some of the things that you might be doing is controlling lights to go on or off, maybe using hand gestures to interact in a certain way, maybe making a face blink. So there might be some computer vision aspect to it. There might be some microcontroller to make something happen. Maybe you make something spin. I don't know, it depends on your robot. There's been a lot of natural language processing recently, like LLM models. So other options, I've worked on augmented reality systems where you need to be able to use a hand gesture to figure out how do you do something, but what's intuitive, like using a enlarge it. Like usually this is used for selecting something, so you can't just use the same thing for make it bigger like you would on your phone. So you got to kind of pick, you know, do I do this? Like figuring out what to do interactively with other humans with your device can sometimes be really counterintuitive and complex. Controls engineer. So this is probably the closest to an electrical engineer, where it's still a software engineer, but you have to be very electromechanically inclined and really need to understand the mechanics of what's going on with the robot. So if you like that electromechanical side of things, but you still want to write code, then this may be a good fit. If you're studying computer engineering rather than computer science, maybe this is a good fit. For a controls engineer, you still need to write C++ algorithms, but not nearly as complex. So you need to kind of maintain the state of things. For an autonomous vehicle, you're going to need to control the motors and the movement of things. If you're dealing with something with water, you're going to have to deal with sensors and pressure and temperature and heating. Maybe you're working with an automated coffee machine. I actually got to use one of those at the airport in San Francisco, of course. But if you're working with an automated coffee machine, then you might have to deal with the pressure and the temperature and timing. So all of these are very important features and factors to make sure you're keeping track of, maintain the state of, and then control the system in the way that it needs to perform adequately. And this is what we would call a lower level software engineering task, compared to higher level, like path planning versus controls. Sometimes those are combined, but they are separate tasks. The path planning is a higher level, so it's further away from the hardware, whereas controls is lower level, you're closer to the hardware and dealing with what's actually going on. User interface is going to be the highest level, where you're closer to the user that is interfacing with the robot. You definitely want to have a really strong foundation in physics, because often the things that you're controlling have physics properties that you need to understand to be able to control them. Whether it's something that moves, like gravitational physics and motional physics, or the waters, if you're underwater, then pressure physics and density physics. So drivers, if you're the person that likes bits and bytes and just getting into like binary and data flows and also getting pretty close to the hardware, then I would definitely say that drivers is a good choice for you. What drivers is it's like controlling input from sensors. You have a driver for the camera. It helps connect the data that's coming from the camera to your computer in a usable way, or from the radar to your computer in a usable way. You may need to take packets out and parse them and convert them into a more usable format rather than in binary format. Drivers can deal with straight C or C++. You need to be able to check for like hardware failures, as well as just consistency and timing management, I guess, of data. If you like bits and bytes, all you. New device bring up. So you need software engineers to be able to take all of the bare hardware, be able to flash the drives with the operating system that you need. So you want someone that can create that initial binary so that you can create an image of that. You want to make sure that the networking is properly set up. Sometimes each of the different robots will get their own IP so that multiple can communicate on the same network and they don't step over each other. You want to make sure that the bash scripting is set up in Linux. You need to be really good at Linux and understanding the whole Linux system, how things work on Linux. You may need to set up passwords. You may need to put licenses on. You need to interact with different sensors so that you can get their IDs to then populate IDs for a particular device. There may be a certain set of initial tests that you run after you've brought everything up to sanity check and say, okay, yes, this is a working robot. You're not going to be doing a lot of like C++ core development. You may be writing the tests. Tests can often be run in Python, so if you only have Python experience, that might be a good fit. Being someone on new device bring up, that might be an easier to get into job because you don't need quite as many high technical skills. The tests that need to be run may already be written for you, or you might be writing them yourself, so it could be one or the other. At one point I was doing new device bring up and I had like 20 different computers, like Xavier's on my desk. Maybe it was TX2s, but the NVIDIA type. NVIDIA. I say that wrong every time. Yes, you can laugh at me. So I did new device bring up at one point and was configuring the networking and the bash scripting and setting the IDs and shadow parameters in the cloud. It's often just following certain steps to be able to make sure certain things are done correctly. You got to be somebody that doesn't mind repetition, because this is something that happens often over and over and over and over and over again. So if you want a job that has a lot of repetitions and you just do the same thing over and over and you don't have to think a lot, this is a great fit for you. Path planning. So path planning is one of the most complex algorithms that don't directly deal with any of the sensor information. Path planning is how you tell your robot to get from point A to point B, and how to dynamically adjust to the situation. So you have all of the static information, that you get from your sensors, like you need to be able to move around a bookshelf or to move around a stop sign. You need to consider the stop sign and react to it actually stop. But then you also need to consider dynamic things that are moving in your space, anticipate how fast something's going, what direction it's going, so that you'll know if you move at this pace at this time, you'll have a collision. You need to make sure you avoid that. So there's a lot of moving pieces with path planning, and you'll need to be able to take all of that information in and program around it. You want to be really good at physics. There's torque that comes into play, and traction, and how does the wind affect a drone when it's moving. If you're programming an autonomous vehicle, you want to make sure it stops in time before, it would hit the car in front of you. You'll generally need to know C++ algorithm development, particularly dealing with trees and graphs. And you want to be familiar with Linux. The most basic is the A-star algorithm. You'll want to have implemented that. MCI and MPPI, be familiar with those. Being familiar with like motion models and kinematic models. You'll want to know how to do multi-threaded development, and machine learning models have more recently been implemented in path planning algorithms, so reinforcement learning in particular. And then you'll want to be able to write tests for your code. Next, we have manipulation, and some would argue that manipulation might be put under path planning, but I would say that it's kind of a different task than path planning. And I don't know that anyone calls it manipulation, that's just what made sense to me. But it's basically like the fine motor skills that are necessary in actually accomplishing the task that you're trying to perform for robotics. So with a robotic arm, what manipulation might be is you can pick whatever it is up that you need to appropriately. And there's like an art to that of doing it precisely. If you have an autonomous delivery bot, opening the doors to be able to allow the customer to pick whatever their thing is up from the inside. If you have a surgical robot, that is the core function of what you're doing. You need to make sure that you're properly stitching, I guess, the person's body. So that's like the most important part. Yeah, I guess manipulation for a drone might be basically just, there's some drone delivery bots where you have to determine, okay, I have this package and I need to make sure that I release the package at the appropriate time. So that might be the manipulation piece for a drone. If you release it too early or too late, it might get stuck in a tree and there goes the point of the package. Skills that are necessary. Because this varies a little bit, it may vary on skills, but I would still say taking sensor information, being able to use that in algorithms. Really, if you get good at C++ algorithms, Linux development, multi-threaded development, linear algebra, then you have a really solid base to be able to work in a lot of the core robotic software engineering jobs. Because manipulation is so like front and center, the core problem of what you're trying to solve oftentimes, then that's often connected to the business people and the people that are like very top heavy, very focused on how the robot's performing. A lot of times there will be pressure on you to make sure that it's performing correctly. And sometimes it's because of what you're doing that's not performing. But there's a lot of algorithms that, manipulation depends on, that if they're not doing well, then you need to have the skills to be able to differentiate, okay, this is how my algorithm's performing versus this is how other algorithms are performing, and be able to see what's the difference, because they'll come after you if they see that your thing is not working. You're in the hot spot if you're working on manipulation. So remote control, I have worked on this one also. It has a bit of a different twist because you need to be able to do the algorithm development on the robot side, which is often in C++. You'll need to be really good at networking because you'll often write sockets to be able to communicate and send messages between the robot side and some type of web platform that you're likely making on the user interface side. So you want to be good at web development, which is more like JavaScript. I feel like the overlap of people that are both good at C++ and JavaScript is probably really small. So you'll also have the component where you're interacting with some type of controller, whether it's like a game controller or like the full-on, put your head on, have the foot pedals and be able to actively simulate like you're moving or driving something. I've also seen remote control be done through an app. So it may be that you're not doing JavaScript, it may be that you're doing app development, which gets more into like straight Java. Depending on whether you're in iOS or Android. So for Android, it's more straight Java, or getting like Unity skills to where you can develop for both and then deploy to both platforms. For iOS, I think it's Swift. I have not done iOS development. I've done a little bit of Android. But basically being able to communicate from whatever it is your controller is to the robot and being able to handle and say, okay, go ahead and do this. So that one gets a little bit more complicated, but I think networking is probably the biggest differentiator. If you're really good at networking, you want to understand like what subnet mask is, what buffering is, what happens if you drop connection, what do you need to do to the algorithms? And then regain connection, you want to make sure that you're not sending old messages or else your robot's gonna like go run through a wall. Yeah, I never did that. So you want to be familiar with setting like Etsy network interfaces on the Linux side. You want to be familiar with Wireshark so that you can monitor messages and packets that are going through on the networking. And you want to be familiar with security. Like, I feel like that's something that's overlooked often, but making sure the messages are encrypted if they need to be encrypted, or they're just in a state that somebody can't just like steal your information if they're being sent remotely. Systems where remote control get really, really crucial are like if you're doing a remote surgical procedure, then you really need to monitor and see, do you have any latency? If you have latency, is it consistent latency and at a low enough rate that you can still reliably depend on your robot? I will say remote control is pretty gratifying just because you get the like physical feedback, the sensory feedback of, okay, I'm pushing this button and this is actually happening in the real world. So if you're one of those people that just love that gratification of, you know, physical thing and then reaction, then that might be a good job for you. Next, perception. The tasks of a perception engineer is to process the information that you have from your sensors to be able to make it more usable for the other algorithms in the system. Sometimes those tasks are recognizing what's in the scene. We'll get into tracking in a minute because that's kind of a separate problem, but you use perception information with tracking. Yeah. Sensors for me are like candy in a candy jar. It's whenever I see a robot, the first question, you know, especially if I like judge first robotics, it's what sensors do you have on your robot? That kind of gives me the insight of what is your robot capable of, what kind of inputs are you getting so that you're able to write the algorithms to be able to handle those sensors. Examples might be recognizing line information, so you make sure an autonomous vehicle stays within its lane. It might be recognizing things so that you won't collide into them. You might want to use it for an occupancy grid, so using some sensors that are short range and other sensors that are long range, and using sensor fusion for being able to pull that all together and say, okay, these are the spaces that I think in my world are occupied versus these are the spaces that I think are unoccupied, and we can use for path planning to be able to route a path from point A to point B. Ooh, what gets interesting for perception is when you need to recognize something over time. It's like behaviors or attitudes or a traffic light, you know, it's currently red, but is it consistently yellow or red, or is it blinking in a state of like, okay, I'm broken, so operate in a different way. So understanding over time is definitely a lot more complicated, but more interesting of a problem. The most common sensor is the camera. So we have a lot of computer vision, machine learning algorithms, deep learning that you need to be familiar with. And the most common frameworks are you have PyTorch and you have TensorFlow and Keras. Those are implemented in Pythons. You want to be really good with Python and those types of data flows and pipelines. So labeling the algorithms, data management, actually creating the machine learning models, understanding what's going on when machine learning models fail, being able to tweak those, being able to look at analysis and produce, this is how my model is training, how do I adapt to that? How do I make changes? Do I need to change the model? Do I need to change the data? It takes a lot of GPU, so sometimes you'll be able to run the local compute, but you also really want to be familiar with the pipelines that are available in the cloud. So both AWS and Google Cloud have systems that'll help you be able to train the full pipeline for machine learning. And you'll be able to leverage GPU, and for Google, they have TPUs, tensor processing units, that are particularly helpful hardware for machine learning algorithms and deep learning. So deep learning has really just taken off over the last 5 to 10 years, and so many people have gotten interested and have really been working in it. So this is a very dense populated field. There are a lot of use cases, so both in robotics and in web. Facebook's using, you gotta recognize the person and, you know, try to manipulate images on the people and try to make connections between things, recognize things that are happening in the scene. With advertisement, they're using it. There's a lot that's going on with generative AI for perception engineers as well. I definitely recommend learning some of the classical computer vision algorithms. There's a lot more than just deep learning. You can learn some of the signal processing techniques, removing high frequency from an image, convolving a matrix or a kernel with an image to do pre-processing techniques like blurring or edge detection or whatever it is you need. Maybe you can use the Huff transform to be able to find something within your image. So images are really good for discerning this between this and what is this, and being able to use the color aspect of, you know, what's in the scene, being able to describe things, recognizing objects. So cameras are really good at getting 2D information, They're not really good at getting three-dimensional information, the size, the shape, the depth. You may be able to get a little bit better using stereo vision, using the epipolar plane when you have multiple cameras at different angles, and then you can get more depth. We'll often get better information with LiDAR if you have the compute to be able to handle it. 3D deep learning has definitely been growing, recognizing things within a scene, doing filtering on LiDAR information, using trees to more optimally process the LiDAR information. There's drone companies that use audio information that you can use for telling like where something is. So if you're using audio, you want to do more signal-based processing. Next, we're getting into the tracking problem. And generally either you want to use tracking for avoiding something or you want to use tracking for kind of monitoring something. So tracking I've worked on quite a bit. So you want to detect the object, which that may be on the perception side. You'll have all of your objects, for each frame that you'll have coming in, and you may have like different stages of association. If you need to establish velocity, then you may need to do frame-to-frame association with a certain sensor prior to it going into a sensor fusion. But then you get into the sensor fusion association stage where you're trying to associate this frame to this frame, but then you'll have all your existing targets that you need to bring in. That gets into the combinatorial problem where you go, okay, how many different possibilities can you have? So you might add the gating. Anyway, it gets very complex. You want to be good at C++ algorithms, multi-threaded algorithms, probabilities, because there's Bayesian statistics in there, tracking, so that's Kalman filter and particle filter, kind of like localization. There's some overlap there. Efficient code writing. You always have a lot of code that always needs to run faster. And of course, Linux development. Something that gets interesting with a lot of these, like tracking and path planning and localization, is being able to test it. You'll often need to write post-processing testing suites that allow you bringing in some type of ground truth, being able to compare to your information that's happening and be able to come up with analytics and say, this is what I think is happening, this is what might be going wrong. And sometimes a lot of the testing actually happens on the fly, like through visualization. If you can see what's happening while you're running it and you have the intuition on what's going on, sometimes that's the easiest way to fix things. It can get complicated, and going from iteration to iteration, it can also get complicated on which is better from this stage to this stage. So you want to move in a forward direction. If you want to do some programming at home, kind of create a project, but you don't have a robot and you don't have any data, I would definitely recommend checking out New Scenes. They have a lot of data from autonomous vehicles that you can take and use for a project, available for free. So next we're going to talk about calibration engineer, and this is really important. So some would say calibration engineer would fit under perception. I wanted to separate this out because it's such an important task on its own and it has very particular applications. So calibration engineer is where you're dealing with the sensors that are on your robot and you want to make sure that they're calibrated. So that means, you want to make sure the position that you have for each of the sensors are correct in relation to each other and in relation to like the center point of your robot. And that would be the extrinsic calibration. There's different ways of doing this. You might see people for camera with the checkerboard pattern where it can recognize where each of the corners are. For LiDAR, you might need to do some type of ICP to align point clouds between each other to say, all right, this is where they're aligned. It's basically saying, these are my sensors, this is where the positions are, and if the positions are wrong, then the algorithms that are working downstream taking those inputs are going to be wrong. So it's just a question of how wrong are they, and are they really impacting things to where it's bad. Things have to be periodically recalibrated depending on what your system is, how much it moves, and how much things shake. So calibration engineers also need to be good with algorithms. I think it's less particularly C++. It probably could be C++ or Python because this is something that runs off the robot. Generally it's not running while the robot's actively running, though it could be. Oftentimes you run calibration prior to running your robot just for sanity check that everything's good. Definitely like on first startup, and then other times is like when you ship the robot, or if you know that it got knocked into, or it seems like the sensors seem off. Like when looking at post-run data. So a device manager or executor is somebody that's going to write a program that can manage how all of the different algorithms are going to be running. It manages the processes, it manages the memory, it manages the CPU, GPU load, so it keeps track of what's actually happening. It manages the system to know, okay, are we overloading our CPU load or overloading our GPU load? Are there threads? If something fails, do I need to bring the whole system down in a certain safe way? That person needs to basically kind of have the high level overview of these are what each of the different systems are, this is how they run. They need to be really good at multi-threading. really good at understanding how the operating system runs, understanding how to manage the CPU load and the GPU load, and making sure we don't go overboard on that. So understanding full system diagnostics, I guess. And with that, it can be really useful to export that diagnostic information so that you can see plots over time to see if something happened over a period of time. Was it just the system that was like too high of a CPU load that was reacting in a weird way so that ended up having these weird functions? User interface. So it depends on where that's implemented. If it's implemented in the cloud, then that'll be something like JavaScript. If it's a computer desktop, that might be straight Java. If it's implemented on a phone, then Android, it might be straight Java, and iOS, I think that's Swift. So with user interface, you definitely want to be skilled at kind of having that eye for what looks good and what's useful, and having that intuition on what is it your user needs to do, and putting it together in a very clear, cohesive way that you don't want it to be overcluttered, you don't want to have too much information, you want to have all the defaults, what most people would want to see and use, so that they don't have to figure out, why is it not working, what do I need to change? Make it easy for the user to be able to look things up. And good documentation. Oh my gosh, good documentation would be amazing at every level of software engineering. We do not have enough people that are really good at documentation. If you're writing the user interface, you may need to write really good documentation for the user. So if you're writing in C++, and you'll want to have Qt experience, that is like the GUI that you work with. If you're writing with Python, I've used tkinter. Web development, I have not done, so I can't go too much into that. Simulation engineer. A lot of times simulations will be necessary to add as a step in testing, and it's really useful when you can see kind of the 3D step of what's going on with your robot and how it interacts in a perfect world. To sanity check and say, okay, my algorithm's good in the perfect world, so let's see how it performs on the regular robot. To be able to create that perfect world, you need to create the simulation. The three most common that I've seen have been Gazebo. So Gazebo is independent of ROS, but it was built in a way that it's supposed to work with ROS. Gazebo Simulator works with C++, Python, Node.js, and JavaScript. I don't know, I had good experience with documentation with ROS. I feel like there was a lot less documentation on Gazebo, so it was more complicated to get up and running. Unity, I've developed in Unity that's in C# commonly, and then sometimes you can add extra C++. There's a lot of user interface interaction, which has physics models embedded into it. They have a really neat like rollerball first tutorial, at least they did like 7 years ago. I don't know if they still do. They have other tutorials I've seen that you can basically get in there and just start going through the tutorials one at a time and go, all right, now I have the experience in Unity, I'm familiar with how this stuff works, and I can start making my own game or module or whatever it is you want to do. Unity is fantastic because you can use it for lots of different things. You can use it for game development, you can use it for app development, you can use it for simulation, AR, VR development as well. Anything that you need to get physics applications for quickly, Unity is a great option for. So if you're gaining the skills, you can reuse it in a lot of different areas. Unreal I haven't used, but I have heard a lot of similar parallels on that. So Unreal is the third option you can use for simulation. Yeah, so something else with simulation, you commonly might need a GPU to be able to do a lot of the image processing and rendering. You do want to be really good at multi-threaded techniques, because something that I've seen is if you have simulations of everything happening 10 times a second, then it's going to be bursts of changes 10 times a second, and that can bog things down. So being able to separate processes so that you have an interval to where you have 20 times a second things happening and they're like every other 1/20th of a second. If you're a simulation engineer, you might end up really benefiting from being able to work in CAD, getting 3D models, turning those 3D models into something that you can use within the simulation. So that's not always a requirement, but if people see that, they're like, oh yeah, you can do that, that's great. Data analyst. This could be just given to every different engineer and used by every engineer to be able to look at their own data, to be able to discern what is the problem, what are the trends, what do I need to fix, and then to go back and fix that in their own algorithm. At the same point, there may be certain statistics that you want to see as a full system, and it may be useful for somebody to basically take all of the information, convert it into a data analysis script, so you can see post-analysis on what your system's doing, so that you can understand the whole impact or find errors within your code. A data analyst is definitely going to want to have some skills in plotting. It's probably going to be a lot easier in Python. You'll want to set it up so that every time a robot docks and offloads all of its information and syncs, the information will go up in some automated system and then be able to be processed and stored somewhere, likely in the cloud. It'll be sent through all of these scripts that can be used for generating plots, generating analytics to be able to see how the system's running over time. If you're a data analyst, you may also want to be really good at talking and communication and explaining things, because if you're the one creating all the plots, other people are going to want to know, what are these plots? What do they mean? Why are they useful to me? Maybe if you have a robotic arm, you want to see how many things did we package today? How many things did we fail to package? How many attempted pickups did we not go through? For a forklift, how many picks and places did we end up succeeding? Maybe if there's somebody monitoring, maybe they would be reporting any bugs or errors, or if the robot itself is reporting any bugs or errors, that'll need to be brought up in okay, CPU error this time. You want to be able to plot that and see, okay, this is what's going on with the system, this is how often we have a problem, so that elevates the priority of this problem because it's happening way too often. You have to have some type of interest in looking at lots and lots of data, being able to clean up the data, being able to find a needle in a haystack sometimes if you have errors. You want to have really good reasoning skills. You want to make sure you have the fine details down as well as be able to see the big picture. I really like the bokeh plot for Python. It makes it really easy to make it interactive, which can be nice. So know as many graphing libraries and the ins and outs when you would choose one versus another. Kaggle might be a good place to start looking if you want to create a project for being a data analyst. There's a lot of freely available data sets on Kaggle, so going on there, you can just download the code, you can try to process, generate as many plots as you want, and kind of see what kind of information might be useful about the data that you're looking at. And you've got to have an eye for, like, what do people want to see? How can you make it most succinct? Put things in the right spaces on the right page, add tabs when necessary, that kind of thing. It seems like engineers are kind of organized in our heads and not necessarily extrovertedly organized. Our desks will be a hot mess, but everything that we know that we're doing, we know we need to be doing, is happening in an organized fashion in our heads. We just don't convey that. So you need to be somebody that can convey organization to other people. Optimization engineers. So I will say, a lot of times you don't specifically have optimization engineers. It's kind of an added skill set. Every system that I've run on has run into okay, we need to fix something so that we can make everything run because we're bogging down right now. So this is really important, and some of the jobs I've seen pay ridiculous amounts of money for somebody that's really good at this. I have seen jobs specifically for optimization engineers, like someone that writes CUDA code, someone that speeds up existing code. You want to be able to write C++ algorithms, know the ins and outs so that if you restructure it in a certain way, it'll make it faster. You want to know data padding if you're trying to optimize sending messages, like the order of how you structure your message types is going to affect the size of the padding. You want to be good at compression. You want to be good at writing the CUDA code or writing any type of optimization to where you can make things run faster. OMP parallel. You want to be really good at multi-threading. You want to be really good at high-level architectural understanding so that if you were to restructure something, it would make sense. So there's things like, in ROS, where if you want to send messages between one node and another node, it'll make a deep copy. Whereas if you're nodelet, then it'll just send the pointer to it. So knowing those little ins and outs can make a big difference, especially when you're talking about copies of full-on point clouds. So a lot of the things that might add complexity to your system, but is necessary to make it run better and faster. So the last on my list of numbered ones before we get into the odd ones are testers. Testers are hugely important. You want to be somebody that can think about, how does the whole system run and how can I break it? And sometimes people love breaking systems. They love going, oh, I caught something. I got a bug. But it's really valuable and useful because if you can catch a bug in the testing system, then you can be able to report it to the engineers, the software engineers that can then take a back look at the algorithm and then try to find the problem. But you have to be very detail oriented, because if someone says, this happened and it was a bug, but you don't have any information on what you ran, like the version of code that you ran, the situation that you ran it in, like what was the weather like, what operation mode were you running in, all of the little details that might affect the system, then it's really hard for the software engineer to be able to determine, okay, what was the cause of the error? And sometimes you're trying to fix something you don't completely understand because you don't have all of the information. So it's really important to be organized as far as logging information. Testing, again, does not require the hard development skills when you're just out there walking with a robot. If you like to be physical and be able to be up on your feet a lot, this might be a really good opportunity. Somebody that's just getting into robotics and really doesn't have any experience, testing is a great opportunity to get in the door. You don't need to be able to develop yet. You just need to be able to sometimes just stand there and follow procedures and say it worked or it didn't work, and then write down all the details. You do need to have really good communication skills so that we can understand exactly what went wrong and how. Now, that being said, testers have a huge range from very beginner testers versus really, really experienced testers. I've actually heard of people using generative AI to come up with test scenarios. Oftentimes, Python is heavily used in testing. Unit tests, you'll probably be running your C++ or whatever code it is you're writing the algorithms in. G-test is a very common construction if you want to learn the Google test framework. That can be a nice, easy way to set up and get these things to run for testing. Jenkins can be really good for automated testing, but that gets more into DevOps. You have simulation testing, so there's actually developing the simulator, but then there's coming up with test scenarios. You kind of need to work with the simulation team to come up with those test scenarios, but just making sure each of those scenarios are covered under testing. There are certain types of robotic systems that can be really hard to go out and test certain scenarios. So you don't want to run your robot near the edge of a cliff. It might be really expensive to collect a lot of data and go through a lot of the testing. So if there's ways that you can set up testing without going out and doing all of the physical testing, that can be really useful. You may need to create a test rig. So sometimes you'll need specific hardware that's useful for instance, if you're testing a tracking system and you want to get ground truth data, you want to record, this is the ground truth data for that thing that we're tracking, to be able to say how far off are we. And that can get really complicated. You do want to be creative and think of how others might use it that don't understand ramifications of the system. A lot of times when it gets into users' hands, they'll start doing things because they don't know anything about how the system works. And you start thinking, oh, that makes total sense that you would do that, but nobody had thought to do it in testing. So you want to be that guy that thinks about doing that in testing. I guess in testing, it is really helpful to have some understanding of the algorithm so that you need to know who to report it to if there's an issue. Jira. Everyone should be using Jira, but testers should be familiar with Jira because you'll want to write out bug reports in Jira and say, this is what happened, this is the day, this is the robot, this is the version of code. This is the scene and scenario. If you take pictures, they probably love you because that'll help, or have the recording onboard logs. Onboard logs, yes, get onboard logs. That makes it a lot easier to be able to run back through, especially if you have a deterministic system. If you run it through your system, you'll get the same error every time. That makes it a lot easier to definitively say, yes, this problem is solved, we can move on. So the last two double sets, so basically 4 more, I have 2 categories that are kind of bonus out in their own. One category is going to be better at dealing with people. So one is a customer troubleshooting, which does not sound like fun, but basically hearing all of the problems and trying to help customers work through their problems to be able to understand what is the core problem and how can we help the customer be able to get through that problem. To be good at this, you really want to be good at communicating, good at thinking on your feet. If you're somebody that interviews well, that might be a good fit. You don't really craft your whole architecture and coding algorithms. Instead, you're listening to the customer, trying to discern out of your understanding of the system what might be happening. You need to have a good memory because if you have noticed, oh, this has been a problem before, then you can bring it up again in memory, and be good at documentation. So if you start noticing common problems, you want to be good at writing down, okay, this is a problem that happened, this was the reason why that problem happened. And that way, if anyone else experiences the problem, they can look up in the log of common problems in your beautiful documentation, this is what I need to do to solve it. Next, customer integration and sales engineer. This is also not someone that's going to be sitting down and writing algorithms, but it's really important for someone to be able to communicate with a customer and see how can our system integrate with your needs. If it's a forklift, how does this forklift work in your factory? What are the things we need to know about your factory? Maybe it's too large a size and we need to adapt our algorithms so that it can work there. Maybe you don't have any networking, so we need to know that we can't just send something over Wi-Fi. If it's an autonomous delivery bot and you're working with a customer that has these steep steps, or Maybe they want to integrate it into their app so that people can choose, I want this at this time, and yes, I want an autonomous delivery bot to bring it to me. So the customer integration and sales engineer both should go out and anticipate what are the problems that we need to know that we can handle before we're integrating, and what is it that's important to the customer so that we know what to present and what to highlight so that the customer's interested. So the final two are the managers, and we have personnel managers and we have technical managers. Some companies have both of those kind of integrated and they don't focus as much on the personnel managers. Some have them completely separate. People that are personnel managers, you want to be good with people, you want to be empathetic, you want to be able to keep in mind both the goals of the project and what they're working on, as well as what are their personal goals. What is it that they are wanting to work towards? Are they getting their needs satisfied? Because when you work on a project, losing people can really set you back and create holes and gaps in your development. You do want to keep people in mind and make sure that what they're working on is leading towards their goals as well as your goals. You don't want to put them in something that they are going to hate because they're not going to stay. A technical manager is going to care more about what are the milestones of our project? Are they being met? Are we giving the tasks to the right people? Is the timelines aligning? Are there any barriers? Do we need to try to fix something so that somebody's not blocked? The technical manager will make sure if there's a solution being implemented, it's the right solution. And if it's not, then what do we need to do to change that, evaluate that, fix that? So I really hope that this was useful to you. Please consider liking and subscribing, and we'll see you next time.